for Xilinx in the AI products team. And along with me, I have my colleague Abid, who is a senior engineer, and we'll be talking about mostly around Vitis AI, and also giving you a demo of how things work and how to, where can you find it, and if you have to try it later on, how to proceed, basically. What I'm going to do today is, because there was not enough time, so we have a pre-recorded presentation, which was done by actually an expert team at Xilinx. It is the Xilinx training team. So we'll be playing a pre-recorded video, which will give you some basics of what Vitis AI is, and then after that, in the second part, we'll be giving you a full demo of the Xilinx tool flow. So let me just start with you. I'll share my screen. I guess you're able to see my screen?
Yes.
Okay, I'll also share the audio so that also gets. Okay, so, and if you have any questions, feel free to ask in the middle as well. We can pause the video and answer any questions that you may be having. So it's important to make sure that everybody understands all the concepts about Vitis AI. So yeah, please feel free to ask questions. So as I said, the objective today is to understand the Vitis AI development. So Vitis AI is the framework to run AI workloads on Xilinx devices, and we'll understand what are the features for Vitis AI.
Let's
and
begin.
Just sorry. And again, we'll have a demo of the things. So so let's hear the video.
Discussing the industry trends. 1. Performance scaling is now coming from application-optimized architecture, for example, data center, 5G, and autonomous driving. An adaptive heterogeneous platform can provide a more software-friendly environment for these architectures. 2. Cloud and edge application unification requires a unified cloud edge platform for software development and deployment. 3. Deep learning is pervasive in all sectors. For example, deep learning provides AI scientists with DNN optimization for deployment and enables traditional software developers with DNN API calls. Deep learning is increasingly replacing traditional algorithms, and traditional software developers want to be able to use a DNN as part of their software code through a simple API call. Artificial intelligence is evolving rapidly. We have already seen that the speed of innovation has outpaced silicon cycles for ASICs, CPUs, and GPUs. FPGAs and ACAPs can keep up with innovations by enabling flexible architecture. If the specification for your ASIC is efficient at GoogleNet, by the time it comes back, the state-of-the-art has moved to ResNet, which makes it less efficient. The question is how to adapt your workloads accordingly. Only with adaptable hardware can you change domain-specific architectures several times a year on the same silicon device. The Vitis AI development environment is the Xilinx development platform for AI inference on Xilinx hardware platforms, including both edge devices and Alveo accelerator cards. The environment consists of optimized IP cores, tools, libraries, models, and example designs. It is designed with high efficiency and ease of use in mind, unleashing the full potential of AI acceleration on Xilinx FPGAs and on adaptive compute acceleration platforms, or ACAPs. The Vitis platform makes it easier for users without FPGA knowledge to develop deep learning inference applications by abstracting away the intricacies of the underlying FPGA and ACAP devices. Let's look at some of the features that the Vitis AI environment provides. It supports mainstream frameworks and the latest models capable of diverse deep learning tasks. It provides a comprehensive set of pre-optimized models that are ready to deploy on Xilinx devices. You can find the closest model and start retraining for your applications. It provides a powerful quantizer that supports model quantization, calibration, and fine-tuning. For advanced users, Xilinx also offers an optional AI optimizer that can prune a model by up to 90%. An AI compiler that maps the AI model to a high-efficiency instruction set and data flow. It also performs sophisticated optimizations such as layer fusion, instruction scheduling, and reuses on-chip memory as much as possible. An AI environment runtime that enables applications to use the unified high-level runtime API for both cloud and edge, allowing cloud-to-edge deployments to be seamless and efficient. An AI library that offers unified, high-level C++ and Python APIs for maximum portability from edge to cloud. An AI profiler that provides layer-by-layer analysis to help with bottlenecks. And finally, efficient and scalable IP cores that can be customized to meet your needs for many different applications from a throughput, latency, and power perspective. The Vitis AI development environment enables embedded developers, application developers, data scientists, and AI gurus to build and deploy their accelerated applications on Zinc MPSoCs, ultrascale FPGAs, Versal ACAPs, Alveo boards, and in the data center. Note the overlay bins were generated using the Vitis tool based on the application-specific architecture. Let's first understand what overlay bins are. FPGAs are semiconductor devices which by design implement an array of logic blocks with a programmable interconnect. Unlike hardened devices, that is, CPUs and GPUs, FPGAs can be programmed to implement a hardware design that does specifically what the user wants. After the design of the hardware system, the FPGA must be programmed using a binary file. This process is typically referred to as configuration. Furthermore, in a use case where there is fixed functionality and dynamic functionality on an FPGA, the FPGA can be partially reconfigured. In a data center environment, the FPGA is always connected to the CPU via a PCIe interface, and it is always connected to external off-chip memory. Given the above assumption, the FPGA binary can be partitioned into a static overlay, or target platform, and a dynamic overlay, or XCL bin. The target platform must be loaded prior to the loading of any overlay. Xilinx cloud partners have already loaded the target platform, and various dynamic overlays can be chosen based on application requirements. There are two methods to deploy your application using the Vitis AI development environment: embedded deployment, or single server deployment, and scale-out deployment. Click each method. Once you've built your application, the Vitis development environment with the XRT API enables you to download and run your application on an embedded device like a Zinc UltraScale MPSoC. You can deploy the same application on an Alveo card in an edge server. The same application can be easily retargeted by simply changing the target. For scale-out deployment across a large number of servers in a data center, your application and XRT can be packaged in a Docker container as a service and then deployed using Kubernetes. The Vitis environment includes a Kubernetes plugin so that Kubernetes can manage FPGA and ACAP resources, much like CPUs and GPUs. For AI developers, the Vitis AI development environment offers a cool way to implement AI inferencing. It provides a series of deep learning processor units, or DPUs. Let's talk more about DPUs. A DPU is a programmable engine optimized for deep neural networks. You can also think of them as parameterizable IPs pre-implemented on the hardware with no place and route required. An efficient tensor-level instruction set has been designed to support and accelerate various popular convolutional neural networks such as VGG, ResNet, GoogleNet, YOLO, SSD, and MobileNet, among others. The DPU is scalable to fit various Zinc 7000 devices, Zinc UltraScale Plus MPSoCs, and Alveo boards from edge to cloud to meet the requirements of many diverse applications. These are software programmable tensor processors, each optimized for a class of deep neural networks. These DPUs can then be loaded once into the programmable logic. You can then develop your network using a framework like TensorFlow and compile your network into tensor instructions for the DPU in minutes using the Vitis AI development environment. There are two stages for developing deep learning applications: training and inference. Click each button. The training stage is used to design a neural network for a specific task, such as image classification, by using a huge amount of training data. In the training phase, the model will be trained using the different sets of data from which it can learn. This is an iterative process to achieve a better approximation of the desired outputs, but it is also compute-intensive. Training has to be done before inference. The model will be trained using different datasets based on the applications. These datasets can vary depending on a variety of data, such as handwritten digits, images, handwritten characters, etc. The inference stage involves the deployment of the previously designed neural networks to handle new input data not seen during the training stage. Inference uses a trained machine learning model to predict or estimate outcomes from new observations. The Vitis AI Development Kit toolchain provides an innovative workflow to deploy deep learning inference applications on the DPU with the following 4 steps. 1. Quantize the neural network model. 2. Compile the neural network model. 3. Program with the Vitis AI programming interface. 4. Run and evaluate the deployed DPU application. Click each step to learn. By converting the 32-bit floating point weights and activations to fixed point, like int8, the Vitis AI Quantizer can reduce the computing complexity without losing prediction accuracy. The fixed-point network model requires less memory bandwidth, thus providing faster speed and higher power efficiency than the floating-point. It maps the AI model to a high-efficiency instruction set in data flow. It also performs sophisticated optimizations such as layer fusion, instruction scheduling, and reuses on-chip memory as much as possible. The Vitis AI environment offers a unified set of high-level C++ or Python programming APIs to run AI applications across edge-to-cloud platforms, including the DPU CAD X8G processing engine for Alveo U200 and U250 cards, and the DPU CAH X8H processing engine for Alveo U50 and U280 cards. The DPU CZD X8G processing engine is available for Zinc UltraScale Plus MP SoCs and Zinc 7000 SoCs. It allows easy porting of AI applications from cloud to edge and vice versa. Once you've built your application, the Vitis development environment with the XRT API enables you to download and run your application on an embedded device like a Zinc UltraScale MP SoC. You can deploy the same application on an Alveo card in an edge server. The same application can be easily retargeted by simply changing the target. For advanced users, the Vitis AI Development Kit also offers an optional AI optimizer that can prune a model by up to 90%. This step has to be done before doing quantization. This tool requires a commercial license. Essentially, what the Vitis AI Development Kit does is take your trained models and transforms them into an efficient implementation that achieves the highest performance AI inference using the deep learning processor. Let's examine the benefits of the Vitis AI library. The Vitis AI library is a set of high-level libraries and APIs built for efficient AI inference with the DPU. It is built based on the Vitis AI runtime with unified APIs, and it fully supports XRT. The Vitis AI library provides a lightweight set of C++ APIs across different AI tasks such as image classification, object detection, and semantic segmentation. It enables easier application development with optimized software codes. It also provides memory management and interrupt handling based on the Xilinx Runtime Library, XRT. The Vitis AI library provides an easy-to-use and unified interface by encapsulating many efficient and high-quality neural networks. This simplifies the use of deep learning neural networks, even for users without knowledge of deep learning or FPGAs. The Vitis AI library allows users to focus more on the development of their applications rather than the underlying hardware. The Vitis environment provides a comprehensive development platform to build, run, and analyze your application. Software application development is done in the context of a platform. What is a platform? A platform is a pre-configured system containing platform I/O, memory, and lifecycle management functionality, and provides a high-level standard API for software. To build an application, the Vitis environment offers dedicated compilers that target the different heterogeneous components in Xilinx devices that include ARM processors and programmable logic in the UltraScale family. High-level synthesis takes your C++ code and automates many of the underlying hardware architecture optimizations. A system compiler then links these individual blocks of code together and creates all the interconnections for optimizing the data movement between them and to custom memory hierarchies. The tool integrates the x86 toolchain for PCIe-based systems and cloud-based target platforms. The Vitis environment also supports edge-based platforms targeting Zinc MPSoC UltraScale Plus devices. To deploy your application, the XRT library provides platform-independent and OS-independent APIs for managing device configuration, memory and host-to-device data transfers, and accelerator execution. Once you have assembled your first prototype, you can simulate your application using a fast transaction-level simulator or a cycle-accurate simulator and use the performance analyzer to optimize your application for best partitioning and performance. Once you have achieved the desired results, you can deploy on one of the target platforms. Let's now discuss the Vitis AI development environment flow, including the hardware platform development. We need to first build the model, then build the hardware, and finally build the software. Click each step to Building the model is a three-step process. First, the trained model from frameworks such as TensorFlow, Caffe, and PyTorch will be given as an input to the AI optimizer. This step, though, is an optional one. The AI optimizer requires a license. With this model compression technology, you can reduce model complexity by 5x to 50x with minimal accuracy impact. Deep compression takes the performance of your AI inference to the next level. Secondly, by converting the 32-bit floating point weights and activations to fixed point like int 8, the AI quantizer can reduce the computing complexity without losing prediction accuracy. The fixed point network model requires less memory bandwidth, thus providing faster speeds and higher power efficiency than the floating point model. Lastly, the AI compiler maps the AI model to a high-efficiency instruction set and data flow. It also performs sophisticated optimizations such as layer fusion, instruction scheduling, and reuses on-chip memory as much as possible.
Hello, is it audible?
Yes, sir, you are audible.
Yeah.
The platform includes the DPU with the desired configuration based on application requirements and other accelerated hardware functions built using the Vitis compiler. You can also choose the hardware accelerated functions from the accelerated libraries. This process has two further steps. The first step is to build the Xilinx object files from the kernel source code. For C, C++, or OpenCL kernels, the Vitis compiler compiles the source code into Xilinx object.xo files. Multiple kernels are compiled into separate XO files. Kernels written in RTL are compiled in the Vivado design suite using the package XO command line utility, which generates a Xilinx object file, .xo, that can subsequently be used by the Vitis compiler during the linking stage. The second step is that after compilation, the v++-l command links one or multiple kernel objects together with the hardware platform to produce the FPGA binary. The application can be developed using C, C++, or Python and compiled using the GCC G++ compiler. The generated files with the AI runtime libraries and the compiled model can then be linked to generate the software.
Is there a question? I saw somebody raised hand. Yeah,
I want to ask a question.
Yeah, please.
That we can input the C, C++ file. And I have a question that is there any limitation in the coding or any program written in C or C++ can be given as input to your tool?
So it's, of course, there is a specific set of APIs that you would be using to run your models on the Xilinx platform.
Yeah.
So maybe in the demo, we can show you what kind of files, C++ files are these. And then based upon that, we can revisit your question.
Okay.
Would that be okay?
Yeah, no problem. Thank you.
Okay. Yeah.
To facilitate the setup of the Vitis AI development kit, a Docker container is used for Vitis AI environment package distribution. The Vitis AI software is made available via a Docker hub. Two options are available for installing the containers.
At this point, I will take a break basically to take any other questions that you guys may be having. There are a couple of other slides which are not covered in this video, which I'll be going through. But till this point of time, if you have any questions, we can answer those.
Yes, sir. Sir, I noticed that the AI compiler, AI quantizer, was quantizing directly into int 8 from float 32 to directly to int 8. So shouldn't it first check if the accuracy is not dropping? Because especially in regression problems, not in the classifications can perform better in quantizer, but in regression problems it can create a lot of issue in accuracy if I directly go to int 8 without checking the accuracies after quantizing.
Right, that may be a problem, but the thing is that Vitis AI right now works mostly on neural networks, and so CNNs and LSTMs is where we work, and there the quantizer taking the model from float 32 to int 8, it actually doesn't drop the accuracy much. So we have our own algorithms for quantization, which basically doesn't drop the accuracy much.
Okay. Or do I have, as a developer, do I have control over it? Can I, if it is happening, can I control it?
There are some options which we can discuss basically in the demo part. We'll be showing you how to run the quantizer, and in that some of the options we'll be talking about, and we'll be showing you other options which are possible available for the end user.
Yes.
So Sumit, is it because of the DPU is implemented as a processor with the set of instruction, and that's why there is a only certain word length are supported? Is it one reason, or am I missing something?
Not certain word length, but because there is limited memory, and the quantized model would run faster on the FPGAs and will also help save the power as well. So those are the reason we first basically do the quantization.
No, that is fine. But why just to the 8-bit? Is it because of the set of instructions are designed for that?
Yes, it is. Yeah, that also is true. Basically, the DPUs are designed to work on the int 8 inputs.
Okay. Yeah. Srinivas has one question on the chat. The question is, can you use the Vitis AI on the Z board?
We have not ported, so ZCU 102, 104, those boards you can Zinc as MP SoCs you can use, but Z boards, it has to be ported to that.
Okay. So currently means only the MP SoC and advanced boards are being supported.
Yes, right.
Okay. Thank you. Any other question?
Okay.
No. Yeah.
Okay, so let me go to another presentation where I have only few slides which talk about certain other aspects of Vitis AI. This is called whole app acceleration. So in AI workloads, what we see, I mean, it is not just about AI inference, which has to be accelerated, but there are so many other performance critical functions which run before and after AI inference. So those are also kind of very time taking. And if you just concentrate on accelerating the AI inference part, these performance critical functions, if they are not doing well, so basically they can become the bottlenecks in the pipeline. So that's where Xilinx devices do well. I mean, you can accelerate even the performance critical functions before and after of the AI inference as well. So that basically gives you the best performance for the whole application, not just the inference part. To give you some more details, if you, let's say, have taken a network for, say, face detection. So running that on in CPU, the pipeline is like you do some pre-processing, some resize, or some other mean subtraction, some other stuff on that, maybe letterboxing and all. And then you send it to AI inference and then post-process like NMS, etc. So that, let's say, on CPU gives you a throughput of 6 frames per second. But by just accelerating the AI part, the inference part on FPGA or let's say any other device, I mean, you can actually accelerate the thing and get a much higher throughput of, let's say, 30 FPS. But the real thing comes, I mean, you can go even better with accelerating the other parts like pre-process. And just by accelerating the pre-process itself, you basically get 33% more improvement and your throughput can go up to, say, 40 FPS. Now, at this step, you can go further and even accelerate the post-process as well on FPGAs. But let's say you are staying there and then there is no opportunity to accelerate the post-process part. Then the next step is, of course, through the Vitis AI tools, you can do the pipelining and then run multiple things in parallel with the multiple DPUs which have been instantiated on the device. And with the pipelining, you can actually achieve even more. So that's a typical example of the Vitis AI development. And I'll give you one more customer example where the whole app acceleration really helped the end user. So this example is of a customer called Peak Speed. They basically have an AI object detection pipeline on the satellite images. And these images are really, really high size. I mean, image size is very high. So the resolution is like 13,000 cross 13,000. And in that pipeline, basically, the object detection is one part, but even before object detection, there are some processes that happen on the images. So that one major process, which is called ortho rectification, it was basically very time consuming on the CPUs or even other devices. So let's just to give you a ballpark figure, I mean, it was kind of taking more than 4 minutes just to process one image for ortho rectification. And then when it got accelerated on FPGAs, I mean, it was just coming down to 1.67 seconds only per image. So that basically gave a 150x kind of improvement over CPU. And this pipeline, of course, included all other components as well. So overall, application level, the speed up was like 15 times. So this, again, there is this video actually you can find on YouTube as well. So the customer itself has put it there with all more details. So this is one example of, I mean, a major example of your whole app acceleration. The importance of whole app acceleration is kind of visible. Along with that, I wanted to touch upon the aspect of integration of Vitis AI into other frameworks. So there are so many other frameworks for inference. I mean, there are many which are getting popular. Of course, the standard ones are there, like TensorFlow, PyTorch are there. But along with that, there is something called Apache TVM, which is an open source machine learning compiler framework for CPUs, GPUs, and now FPGAs as well, and other accelerators. So without going into the details of TVM, TVM lets you bring in your models from all kind of frameworks and use its compiler framework to run things on different kind of accelerators. And this is the stack that we have for TVM. And as I said, so this is where Vitis AI has been integrated, and I mean, you can leverage the power of Xilinx FPGAs through TVM as well for any kind of models that you're bringing in from other frameworks. Like let's say MXNet is not directly supported by Vitis AI. So if you just directly use the Vitis AI framework for an MX model, you will not be able to do that. But if you're coming through TVM, you can bring in so many other kind of models. And then because we have done the integration of Vitis AI into TVM, you can go through TVM and run your other kind of workloads and other kind of models also on Xilinx FPGAs through this. So this TVM is one example. And other than that, as I said, TensorFlow and PyTorch integrations have been done, TensorFlow Lite and also ONNX. So all these are also, I mean, if you are primarily a user of these frameworks, you can still, without actually spending too much time on kind of running your model on FPGAs, you can use these frameworks and seamlessly run your models on FPGAs directly by writing applications in these frameworks. So with that, we would go to the demo part. So I'll hand it over to Abid, who will be showing you a demo and also showing you the repo, the repository on GitHub for Vitis AI.
Sure, thanks, Sumit. So I will take you through a demo first, which will go through a basic ResNet classification network, quantization, compilation, and then running on the hardware. And after that, I will take you through a tour of the Vitis AI repo and what are all available in the repo. So the first step for Vitis AI, the entry point is nothing but the Vitis AI Docker. So pretty much all the tools comes inside the Vitis AI Docker and it is public. So right now I have already pulled one Docker from the public repo. It takes around, 10 GB. So I already pulled it and kept it here. So if I look at the different Dockers images I have available, this is the public version. But for today, I will be using a newer version, which is not exactly released right now, but it will be released in a couple of days. So I will be using this new Dockers. So, and another thing is that you should have a latest version of the Vitis AI repo. So that again, I have cloned it here. Now I need to start the Docker first.
Abid, sorry to interrupt. Can you just show the repo on the in the browser, maybe just to start with?
Yep. Yeah. So this is the public Vitis AI repo. So currently, as you can see, it is in the Vitis AI 1.4.1 release. But as I said, it within a couple of days, the Vitis AI 2.0 will be released. So this is the repo that you have to clone to start using it.
Thanks.
Yep. So
So by the way, these instructions are whatever Abid is doing to download the Docker and start the Docker are mentioned on the main page of that repo that he showed.
yep, I will show all those things. So I will first show the flow first, and then I will take you all through the readmes and docs and everything.
Okay.
So initially they will show the typical license. I will just give yes for everything for now. Okay, so I have it. So now the Docker is started. Now I want to use a particular DPU instance. So for example, in this case, I am trying to run, just a minute. Yep, I'm trying to run this GoogleNet model using a DPU CAD F8H kernel, DPU kernel. So this is particularly for U200 and U250 model. Sorry, U250 device. So I need to first source my, set up my device for this. So I can just source this device and it will try to find the appropriate devices which are all connected to my machine. So in this case, it found a U250 device. So I'll be using that. It automatically selects the overlap bin path and other firmware and everything. So once I have this, I need to, I'm planning to use a ResNet TensorFlow model. So each framework has its own set of tools. So for this one, I will be using Vitis AI TensorFlow Conda environment. It has all the Quantizer compiling everything pre-installed in this Conda environment. So my Conda is activated. Now I also need to get a few set of images for trying out the network. So I will download a publicly available 500 images ImageNet dataset. It's downloading the images. After that, it will download the ground truth. Yep. So we have got 500 images. Now, so the first step here in the TensorFlow flow is to find the inputs and outputs of the model. So first we have to get a floating point model. So you can use your own trained model. That's fine. But Xilinx, this repository, Vitis AI repository, also comes with a huge set of pre-trained models. So let me see where did I keep it. Yeah. So this is the Vitis AI model zoo. So it's also public. Anybody can use it. So in this one, you can go to the model list, and you can see like almost close to 100 different applications are there. So there is a CF stands for cafe. So this contains cafe models. And if you go down, there is a darknet models for YOLO. And then there's a PyTorch model. But what I really want to use is a TensorFlow model. So there are TensorFlow 2 model and the normal TensorFlow 1 models. So I will be using a TensorFlow ResNet 50 model. So if you open this model, you will get a YAML file, and that YAML file will contain details like this. So the YAML file contains like a different, what is the input size, then which framework it is used to train, and is a pruned network or not. So if it is a pruned network, you will get a much better performance with a minimal loss in accuracy. Now, there is a different kind of model. So in this one, there's a float and quantizer model. So, and here is the download link. So this contains the actual floating point trained model, as well as a model that is quantizer by Xilinx. So if you don't want to train your model, or you don't want to quantize, or as somebody was asking, like you don't want to lose the accuracy, then you can directly take this model and do the rest of the stuff. So in this case, I will be using this zip file to get the float model. Now, if you really don't want to quantize or even compile anything, you just want to start using or deploying the model, there are already a set of pre-compiled models available for pretty much every architecture that we support. So you can directly download them and start using it. So, but in this demo, we'll start with the complete flow. So we'll take the float model. For the
there are a couple of questions on chat.
Okay. Sure.
So first question I see is that how it will help in developing an API. And let's say we have our trained DL model and want to deploy it on edge devices, let's say on mobile phones for real-time inference. So if you already have your trained DL model, you can directly bring it. I mean, there are APIs. You don't have to develop APIs. There are APIs which are provided by Xilinx. So the way, I mean, through this YAML file, you are just getting the download link for the model. So if you already have your model, you can directly use that and take it through the process that we have for quantization, compilation, and deployment. So similarly, the next question is that is there some script to convert? So you don't need to convert it to YAML. If you already have a trained model, you can I mean, take it through the process and run it on the FPGAs.
Yeah, so all these models are already available there. You don't have to do anything. You just click on whatever whatever network you want to. The downloading link will be available there. You can just download and use it.
So Pratik and Rohit, does that answer your question, or do you have any follow-up questions? Okay, if not, maybe we can. Yeah. Okay. Great.
Okay. Yep. So I have the link, and so I will go to my project folder. So it's in the examples, DPU, CAD. So this example comes with the repo. It's already there. You can just anytime you can just download and start using it. Yep. So here, as you can see, I have already downloaded for the sake of time and unzipped it. So it contains, for example, if you go to the float folder, it has the floating point model. And for quantizer model, there is already a quantizer model. One thing you need to understand is that for TensorFlow model, you need to pass a frozen graph. So for TensorFlow 1, you cannot simply pass a typical Python network description. That is not supported. It has to be a frozen graph, and there are TensorFlow API to generate a frozen graph. So it's an easy thing to do. So now I have the model here. The first thing I want to try is to do an inspection. So for that, so I need to use the YQ TensorFlow. So basically, this is the Quantizer tool for the TensorFlow models. And sorry, I put it twice. So I have to pass my input model. So if it's TFS 2.0 float model, and it should be ResNet V1. So this is my input float model, and I want to do an inspection. So what it is doing is that it goes through the entire frozen graph and figure out the possible inputs and outputs from the graph. So now if it is the way we are expected, then we can directly pass this as the inputs and output node. So typically we have, so for these tools from the frozen graph, we have to pass the name of input and output nodes so that the tool can understand where is the input and pass the data accordingly. So once I have the names, I need to use the Quantizer. So the Quantizer has a set of options here. So once again, VIQ TensorFlow is the quantizer, and quantize is the task we are going to do. So input frozen graph, anyway, we know. Then input nodes and output nodes. So this is what we got from the inspection. It should be matching. Then input function. It is a name of a function in this script. So what does is the pre-processing part. So these graphs, this frozen graph doesn't contain the pre-processing part. So to quantize the data, we need to pass a few set of images. And when we pass the images, we need to pre-process the image properly. And the frozen graph doesn't have the information about that. So we need to pass a new function which would load an image and pre-process it properly, and then its output will be passed to the network. So that is the requirement of input function. And then input shape is the network size. And calib iteration is nothing but how many iterations I need to run for the calibration. So the calibration is nothing but passing a set of few images and figuring out different statistics from the network, how the network behaves on different nodes. So in this case, I will be passing 10 images. Now, how many images you have to pass? It's kind of not like a very clear answer. In some cases, for most of our cases, even a 10 or 25 images, it typically works. But in some cases, we have sent more images. It is more like how many images you need for a training. It's like very difficult to answer. So like that, but even for typical all the networks, even with the 10 images or 25 images, it works fine.
Yeah, but if you see some real big loss in the accuracy, you may need to pass more.
Pass more images. Yep. So it is taking each image and passing it to the network and computing various statistics so that the quantizer can convert this float 32 model to an int8 model.
Yeah, there is one more question, Abid. Can you take that up on chat?
Yep. Can we keep on improving our model as we are going to get a real-time, real data? So is it like a online training? I didn't clearly understand the
Yeah,
question.
that's what I think it is. So they're saying, I mean, if you have already trained your model, yeah, online training. I mean, this is not a training tool. I mean, once you finalize your model, then you basically bring it to Vitis AI for inference,
Right.
deployment.
Yes. So Vitis AI stands for like an accelerated inference. So it is not about the training. For training, you can use any model that you have, any framework that you have. But once it is finalized, then we use this Vitis AI to accelerate it. But in parallel, you can use other framework for online training. And if it improves the network, you can do this iteration again to get better network acceleration.
So I have one question here. So this quantizer here, you have floating point model, and from that you are generating your quantized model, right?
Yes.
And here quantized model, your output word length is already fixed, right? 8-bit of word length.
Yes. Yes.
So what it is checking here, like what is the logic? What is happening in this 10 step or with the 10 images? What it is trying to do?
Okay. So on very top level, it is trying to understand the range of the data. Mm-hmm. So basically, we are sending the real images and seeing like the range of data at each nodes or each nodes, and see like what is the range of data. And based on that, it tries to figure out the optimal notation, the fixed point notation for these
Okay.
nodes.
Okay.
Yeah, that's very top level, but a lot of
and
other
is it I think it's not a free tool, right? It's it needs a license, right? Or is it
so whatever I'm showing you right now, you can directly take it and use it.
Okay,
there is no need of license.
Okay.
Only the pruning, for the pruning, I think you need a commercial license.
Yes. Yeah. Okay.
So the quantization is done, and you have the result here. So once you have this quantized model, now as you can later on, somebody was asking, right? You can check the accuracy of this model, and there are some like tools that comes in the same zip file, which to check the accuracy and everything. And if the accuracy falls below what you have expected, then you can even, there are like different methods Xilinx provides, like fine tuning, quantization aware training, quantization aware fine tuning to improve the accuracy. So that all you can do. But for now, we will just go to the compilation and then inference. So the next step is the compilation. So the compiler tool is once again the YC TensorFlow. Here I have to pass the architecture. So remember that the quantization is not architecture dependent. Like it doesn't need to know anything about the device that you are using, because it's like a common to every device. But for compiler, you have to pass which device you want to compile for. So for me, it is like a DPU CAD architecture for a U250 device. Now this is my input graph and the output directory and the output file name, and then a set of other options. So one option is here is that the batch size, so the input shape. So here I'm specifically mentioning the batch size 4, because this device, this particular architecture supports a batch size of 4 in the U250 device. What it means is that you can run inference on 4 images in parallel. So that's the reason we are passing the input shape batch sizes 4, so that the compiler will schedule all the 4 images in parallel and get a optimized schedule. Now there are a lot of other options here also, which you can use to configure the compiler in a lot of other ways you expect. But here I'm taking the simplest version. So this might take a couple of minutes. So in meanwhile, I would like to show you some documentation which will be very useful for you. That is Vitis AI user guide, UG 1414. So this has all the information that I'm explaining right now, like how to get started, how to set up, then how to quantize for different framework that you're using. So in this case, I'm using this TensorFlow on .x. Similarly, you have 2.x, PyTorch, Caffe. Then once after that, how to compile the model and even finally deploy the model. So if you just go to the TensorFlow on .x model, the quantizer alone, if you really go down and see the set of options available, you can see there are like a lot of options here, like how much should be the wait bit and activation bit and everything. So you can really configure all this stuff, but you need to understand that the underlying DPU architecture is for 8-bit. So typically we use all these techniques to really understand, like if we lose the accuracy, then we try with the higher bit width and see if we are actually gaining the accuracy or not, so that we can pinpoint like where exactly the problem with the quantization. And similarly, there are various methods of quantization, like so, and then yeah, it's like a lot of options to explain for now, but there is a lot of stuff that you can just go through. And similarly, if you want to support Rails 6, there is something here, option for that. So similarly for compiler also, if you go through, there are a lot of options the way you can configure the schedule. So in that also like very useful, like if you really want to have like a very rigorous optimization, or you want to relax some optimization like that. It's more like our GCC O1, O2, O3 kind of options. So let us see where it is. This typically takes around 3 to 5 minutes for the ResNet.
So
Yep.
by the way, these steps you don't need to do every time. So I mean, these are kind of one-time things. You quantize, compile your model. Once the model is ready for deployment, after deployment, you are just running your workloads. Then these things are not required.
Yep. So I have the compiled model ready. So now, just like Sumit was saying, actually I could go to my model zoo and I could have directly downloaded the appropriate version for my device. So and directly used this model. I didn't have to go through Quantizer, compiler, or anything. And most of the time, the Xilinx like ensures that the accuracy is almost as same as the float model. So now we have the compiled model, and I would like to use this application here to run the model. So I have a very small application here. So I will just go through that, show you what is there in this. So at top level, these are like a basic stuff. What I really want to show you, yeah. So there is a CPU softmax computation. So basically what it means is that I will be doing my softmax computation on the CPU, not on the FPGA. So this is the post-processing part. And similarly, the top K, which selects the top 5 or 1 entry, again on CPU. Now, this is the actual function where my ResNet 50, run ResNet 50. So it is taking a runner VART runner. So these are the actual VAI specific API that you need to use to run the model. So for example, VART runner is like a wrapper, like a common wrapper for pretty much all the device from cloud to edge, so that the same application can work on both cloud and edge without any change in the code. You just need to change the X model, the compiled model for that particular architecture. And here I'm doing the pre-processing. So if you have used the Cafe or even TensorFlow, you might like this input tensors, output tensors, and so there is a mean value here, which I need to subtract from the image, the resize part. So here is the actual pre-processing is happening. Once again, it's in the CPU. So the mean subtraction and then the image resize, everything. Now, depending upon the computational cost of this pre-processing and post-processing compared to the inference, you may have to think of the whole hap acceleration if you really need to get the full performance of the FPGA. So once I have the model ready, I have already filled the pre-processed data in the buffer, and then I just need to call the runner execute async. So it will take the inputs and it will run it through the FPGA, and the output will be filled in this buffer, and just wait for the until the result is populated. So once I have that, I can directly call the CPU softmax and topcat. That's it. It's like a very simple application. Pre-processing and post-processing remains the same. Only thing you have to plug it in is this runner declaration and then the runner execute async function. So if you go to the main function, are passing our compiled model, and we read that to a subgraph and then use that subgraph to create a runner. Now, all this code remains the same, irrespective of which device you are using, whether cloud device or edge device. It's just that you have to pass the different compiled model. So I think that's all about the code. So I can just build it. So I have the executable ready here. Now I need to pass the our compiled model, which is ResNet 50X model. So this particular X model is like our Xilinx own way of network serialization. Like just like you have the frozen graph or Cafe model or PTH file for PyTorch. Okay, and I need to pass a set of images which I have already downloaded here. which has like some 500 images, and I just run it. So it basically takes all the images from that directory and get it through the entire, yeah, so 500 images is done. So yeah, so this is the overall flow of the Vitis AI, where you can take a float model, quantize, compile, and then deploy it. So are there any questions up to this much? If not, I can give you a tour of like what exactly available on the Vitis AI repository. Okay. I think I will continue with the repository. So yeah, this is the public repository. Now, yeah, one of the very important content of this repository is nothing but a public AI model zoo, which I already showed you. There's like a wide variety of applications you can download and free to use it. Now, if you really don't want the compiled model, you can still take the float model and use it in your applications. There are like a lot of classification, and then SSD and YOLO detection, segmentation. Then there's like a ADAS detection for like actual autonomous driving cars, all those kind of detection, and post estimation. A lot of applications. It's all available. Then so somebody was asking like how the performance, like the quantization, after quantization the accuracy comes down, so how does it look? So this is the top level, oh sorry, not this one, AI model zoo. So here if you go down, there is a model details. So if you click here, there's a details about pretty much every network. So here I want to show you, for example, this ResNet 50, right? So how many ops per image? So lesser the ops, more performance you get. So this is the floating point accuracy, right? 0.74, it's almost like 74.4 performance. Sorry, percentage accuracy. Now this is the quantized model accuracy. Sorry, this is the quantized model accuracy. So if you really see, it's like almost like a 1% drop. Now, if you really use the quantization aware fine tuning or quantization aware training, maybe you will be able to even regain that accuracy. So for and in some cases we have seen that it even improves the accuracy. So you can just go through all this network and see what is the difference in the accuracy, and you will see that the accuracy difference is not much. And that is one thing. And second thing is the performance. So if you really scroll down, you can see how this network performance on all of our architectures on the FPS scale. So for example, ResNet 50 with the end-to-end with a single thread, it is taking a latency of 12.44 millisecond, and you will be getting up to 188 FPS. So like that, you can just check with for every model, you can see what is the performance on each device. So this is for edge. And if you go down, there are like cloud devices. So yeah, feel free to have a look at that. So that's one thing. Second thing is the tools. So the tools contain a set of tools. So for example, here you can see the RNN quantizer. We didn't use this one. So this is specifically for RNN and LSTM networks. Now, another one is like a Vitis AI library. That is something very useful. So it contains like a application template actually for pretty much every application you want to use. So you can see like there's a wide variety of application. So you can just download it, compile it, and use it. The models are already there. Application is also there. You can just take it and run it. And I think we have like a more than 100 applications right now, and still growing. Now, another thing is a profiler. So this is mostly for profiling stuff, like where you can get a nice trace and everything, and how like the various statistics on your execution. So you can see like which one is taking time. Is it like a memory bandwidth problem or a compute problem? All those kind of stuff. And this Vitis AI Quantizer is what we use for right now, the quantization. And this VART Vitis AI runtime is the actual runtime. So when you are writing like a deployment code that I showed you, like for example, the right. So this application, so you can see like all this VRT runner, create runner. So all this API come from that VRT. So this is the place, this is the layer that actually talks to the hardware. Oh, sorry, I didn't understand the question. Is there a question? So these are the various tools available, and this external directory is what Sumit presented at the very end, right? So where we are integrating Vitis AI into the other frameworks that people are using. So you have like a TVM framework with Vitis AI integrated. Similarly, you have a TensorFlow Lite and ONNX runtime. So it comes with its own advantages. Then, so whatever example that I showed you right now is coming from this particular example. So these are like very ready to use example. You can just all the steps that I showed you right now, like Vitis AI TensorFlow, so is download the image dataset, inspection, quantization, compilation, and finally execution. Everything is properly documented here. So if you really want to get your hands on this one, this is a very nice starting point. Now, those who are more advanced, like if they really want to go much more bigger applications, and this Vitis AI demo is the good folder. OpenAI application or IMDb, like IMDb comments satisfaction, sorry, sentiment review. Similarly, customer satisfaction. All these are included in this directory. VRT contains a lot of demos for like a lot of this demos that is available, like segmentation, video analysis, everything. And Vitis AI library I already showed you. You can just go to this directory and compile it and start running it. Now there's a whole app acceleration that Sumit already explained. So it basically accelerates everything like a pre-processing, post-processing, inference, everything on the FPGA. Right now it is in the demo directory, but in the new release, it will be in the very main directory. And I want to have like a quick walkthrough in that. So here you have two folders, mostly plugins and apps. So the apps contain some of the applications out of the 100 Vitis AI library applications, which does the full acceleration of the app. So there is like a ResNet 50 where all the pre-processing, everything is accelerated. Similarly, there is another one, ResNet 50 JPEG, where even the JPEG decoding is also accelerated on the FPGA. So you can just take this and build or even use already available overlay bins and then just run it and see the performance for yourself. Now the plugins directory contains these extra plugins that was used in these applications. So for NMS, it's typically used in the detection network like YOLO and SSD, like non-maximal suppression. Blob from image is another pre-processing step used in the detection. Then optical flow, TVL1 is optical flow implementation, a particular algorithm for optical flow that is TVL1. Now the JPEG decoder, obviously it says like you can for decoding JPEG images. Then yeah, cost volume is for, I forgot the details of this one. I think it's for PSMnet, but yeah, I forgot the details of this one. So yeah, you can just go through this whole app acceleration and you can try like the whole application running on the FPGA. Now, finally, if I come back here, now for the really advanced people, like those who want, so what I'm saying right now is that you just download the compiled model, download the already built overlay bin, and just run the application or just deploy it. Those who really want to go inside and want to build all the overlay bins by themselves and everything, this is the place to go. So here you have the DPU reference designs. So you can just take the design and build it for yourself with the other plugins that you want to use and build your own applications out of DPU over the DPU. So it's all on your, so depending upon like what you want to do. So this is like the quick overview of the Vitis AI directory. I think you'll have a good understanding right now if you really want to give it a try. So are there any questions? Yeah, Sumit has dropped off.
Yeah, so he had some other meeting or something, so he told me that he is leaving.
Yeah.
Okay. Thanks a lot, Abid. Thank you very much for the in-depth explanation about the tool. Any questions? Any question from the participants? Okay. So Abid, so for this tool, as you mentioned that everything is on the GitHub, including the tutorial PDFs, usually documentation. They're all there on the GitHub where anyone can go through them and learn those, right? Or try those tutorial.
Yes. So this particular documentation that I showed you,
Yes,
like
yes,
user guide, that you may have to download separately.
Xilinx. Okay, okay.
Okay, you can note down this number and you can search for it.
Yes. Okay, Pratik has one question. Do we have access to optimize algorithm or optimization algorithm? Pratik, can you?
Is it talking to the pruning?
Yeah. So I'm talking about the optimization algorithm that you are using. So do we have any paper or something, some repo or something where we can find it out, like how it's working?
So is it about the pruning?
Yes, it's about the pruning.
So it's a Xilinx patented one. So,
okay.
But I think they had published somewhere actually.
Okay.
I'm not really sure. I don't have a reference right now for that.
Okay.
Also, does this Vitis AI supports the dynamic function exchange or partial reconfiguration? Is the support is there or it's not there?
I think it is there because I have seen like people doing that for the while building with other kernels. So, but I haven't personally used it. So typically hardware team uses that.
Okay.
And I have seen them reporting like a significant improvement on the building time and everything.
Okay.
Because the DPU building itself from the scratch takes a lot of time.
Yes. Okay, so if there are no questions, thanks again. Thanks Sumit and thanks Abid for your time. And thank you very much for the in-depth tutorial. So I just have a couple of questions. So we have recorded the session. Is it okay to